In this scientific paper, the authors investigate the interactions between nanoparticles, NPs, and Diblock copolymers. While the effects of NPs on polymer matrices have been extensively studied, the effects of the Diblock domain interfaces on particle-particle interactions have not been well characterized. The authors use polymer field theoretic simulations to quantify the interactions between bare and grafted NPs in microphase-separated AB Diblock copolymers. The paper begins by introducing polymer nanocomposite (PNC) materials, which are polymer melts with dispersed nanoparticles. These materials have unique combinations of properties and have been shown to exhibit enhanced mechanical, optical, thermal, and electrical properties. Control over NP dispersion is essential to achieve desired effects in PNC materials. The dispersion behavior of particles is relatively well understood in athermal systems, where the particle surface chemistry matches the polymer matrix chemistry or where grafted chains of the same chemistry as the matrix chains are interdigited. However, the interactions between NPs mediated by Diblock copolymer (BCP) melts have not been as rigorously studied. BCP matrices enable microphase-separated domains, which can be used to control NP dispersion behavior. Previous experimental studies have explored the rich and complex physics in BCP nanocomposites, including the effect of particle size on position within BCP domains and the NP loading at which macrophase separation occurs. Some studies have demonstrated the ability to direct NPs into Diblock domains, which could lead to materials with increased thermal or electrical conductivity along those domains. In this work, the authors perform polymer field theoretic simulations to study the interactions between bare and grafted NPs in Diblock copolymer matrices. They show that for bare NPs with athermal interactions and similar diameters to the B domain, the presence of an AB interface leads to an effective interaction between the particles with multiple minima separated by a free energy barrier. These effects primarily result from chain stretching and compression near the AB interface induced by particle-particle interactions. Grafted chains largely prevent these effects and reduce particle-particle interaction strength. Overall, this work provides valuable insights into the interactions between NPs and Diblock copolymer matrices, highlighting the importance of the AB interface and the role of grafted chains in controlling NP dispersion behavior. The findings have implications for the design and fabrication of nanocomposite materials with tunable properties. Constrained PMFs for bare NPs in cylindrical and lamellar Diblock copolymer domains. The PMFs show the effective interaction energy between the particles as a function of the distance between their surfaces. The primary minimum, energy barrier, and secondary minimum are denoted by black circles. The A-segment volume fraction in 2D slices through the simulation boxes at the corresponding points on the PMFs is shown in figures 1bd. Unconstrained PMFs for bare NPs in cylindrical Diblock copolymer domains. The PMFs are generated from simulations with one explicit NP and one field-based NP. The A-segment density in 2D slices through the simulation box is shown to illustrate the location of the NPs. Discussion of the PMFs for bare NPs in cylindrical and lamellar Diblock copolymer domains. The PMFs show the effective interaction energy between the particles as a function of the distance between their surfaces. The presence of multiple minima separated by energy barriers indicates the presence of complex particle-particle interactions. The effects are primarily attributed to the chain stretching and compression near the AB interface induced by particle-particle interactions. Discussion of the entropic and enthalpic contributions to the free energy of bare NPs in cylindrical Diblock copolymer domains. The entropic and enthalpic components of the free energy are separated using thermodynamic relationships. The entropic effects dominate the interactions, suggesting that chain stretching plays a slightly more prominent role in the system than AB interface minimization. Unconstrained PMFs for bare NPs in cylindrical Diblock copolymer domains. The PMFs are generated from simulations with one explicit NP and one field-based NP. The agreement between mean field and complex Langevin simulations indicates the robustness of the results. Comparison of unconstrained PMFs for bare NPs in cylindrical Diblock copolymer domains at two different AB repulsion strengths. The PMFs show the effective interaction energy between the particles as a function of the distance between their surfaces. The energy barriers decrease with increasing AB repulsion strength, indicating the influence of the AB interface on particle-particle interactions. Discussion of the unconstrained PMFs for strings of fixed NPs in cylindrical Diblock copolymer domains. The PMFs show the effective interaction energy between the particles as a function of the distance between their surfaces. The energy barriers increase slightly with increasing NP chain length, suggesting the possibility of fabricating rod-like NPs using chains of spherical NPs. Discussion of the nematic order parameter and polymer conformations near the particles in Diblock copolymer domains. The nematic order parameter is used to quantify the alignment of polymer chains near the particles. The results indicate that chain stretching and compression occur near the particles, with the presence of the AB interface influencing the conformations. The relationship between the nematic order parameter and the free energy features is also discussed. Discussion of the constrained and unconstrained PMFs for bare NPs in cylindrical Diblock copolymer domains with different graft lengths. The PMFs show the effective interaction energy between the particles as a function of the distance between their surfaces. The differences between the constrained and unconstrained PMFs suggest the presence of a softening effect for field-based particles, while the influence of graft length on the PMFs is also observed. Discussion of the brush and A-block domain density profiles for different graft lengths in cylindrical Diblock copolymer domains. The density profiles provide insight into the conformations of the grafted chains and the influence of the AB interface on the brush conformation. Discussion of the entropic and potential energy contributions to the free energy for systems with grafted NPs in cylindrical Diblock copolymer domains. The entropic and potential energy components of the free energy are separated using thermodynamic relationships. The results show that both entropic and enthalpic effects contribute to the interactions between the grafted NPs. Discussion of the potential energy contributions from AB contact and D-block and brush chains in systems with grafted NPs in cylindrical D-block copolymer domains. The potential energy components are separated to analyze the contributions from different chains. The A-segment density maps illustrate the conformations near the particle and the presence of the AB interface. Discussion of the unconstrained PMFs for grafted NPs in cylindrical D-block copolymer domains with different graft densities. The PMFs show the effective interaction energy between the particles as a function of the distance between their surfaces. The results indicate that the graft density can tune the strength of the NP interactions. The paper focuses on studying the interactions between nanoparticles, NPs, in D-block copolymer melts. The authors used polymer field theoretic simulations to quantify the interactions between bare and grafted nanoparticles in microphase-separated D-block copolymer matrices. They found that the presence of the D-block interface leads to an effective interaction between particles with multiple minima separated by a free energy barrier. These effects are primarily due to chain stretching and compression induced by particle-particle interactions near the interface. Grafted chains reduce the strength of particle-particle interactions and have a reduced extension compared to duetted brush chains. The studies indicate a new route for controlling the dispersion and assembly of nanoparticles in D-block copolymer matrices, which can lead to tunable plasmonic properties in metallic nanoparticles. The findings provide insights into the design and fabrication of polymer nanocomposites with controlled nanoparticle interactions. If you are an author or copyright holder for the work presented in this video and you have any issue with the existence or contents of this video, please let me know.